Hello, my name is Dmitry. Welcome to the DPLABS channel. Today's video will be about testing a motor based on the Slavyanka winding on our test bench. A lot of people would like to know how it actually works in real life. We specifically bought it quite a while ago. We'll see all the pros and cons of asynchronous motors. Why did we start all this? Asynchronous motors, unlike BLDCs, are both more technologically advanced in manufacturing and cheaper. They don't require rare earth metals like those used to make neodymium magnets. And they're assembled using well-known technologies for the same general purpose motors. How should I put it, damn it? For general industrial use, but there are also some downsides. In this video, we're going to break that down. In the previous video, you might have seen our test bench. A power bench for electric motors. So 8.8 kilowatts. 20 Newton meters. Look, it's glowing red hot.
To be honest, I didn't really know.
We actually calibrated it using a Golden Motors engine, which is a Chinese manufactured one, specifically chosen because it has all the detailed specifications provided by the manufacturer for both torque and efficiency. And we ended up getting really good calibration results overall because the error was just about 1% in efficiency and only a couple of Newton meters in torque, according to that same Chinese sensor. This engine is being sent for further refinement. Once it's been improved, we'll take new measurements again. And today we actually really want to put the famous and well-known DA-90 engine, Duyunov's engine, on the test bench. You already know there are a lot of legends about the Slavyanka windings, that it's some kind of unique winding with unique characteristics, a unique engine. I don't want to be biased today, so we'll check it out carefully. It's not hard to test. We'll put it on the bench for evaluation. We have a good controller with vector control, so everything will be very precise and we'll see its actual characteristics.
So now we just need to install our DA-90 motor on the test bench. For this, we need to make brackets for the test bench, because each motor requires its own bracket, and accordingly, we need to remachine the coupling. I've already drawn the front bracket for this engine. There will also be a plate coming from another side at the bottom, which will be included as part of the assembly. We'll weld all of this together, making sure each joint is properly aligned and secure, and then install the assembly onto the test bench for evaluation. This isn't our first motor, so we already have all the necessary measurements and dimensions ready. With this information, we go ahead, cut the parts on the laser, weld them together, machine the couplings with the specifications, and then
our engine will be installed on it. We've already mounted our DA-90 engine on the test bench, and we've also invited Evgeny, who brought a custom-made controller board of his own design. And now, we're going to connect the engine and run some tests.
My name is Evgeny, and I'll tell you a bit about the test bench and in particular about our engine control unit. You could call it a frequency converter, judging by its appearance. It might look like a Nissan module, but in reality it's not that simple. Because a long time ago, we started experimenting directly with the Nissan module. And it had the original control boards, which were very smart, but communicating with them was extremely difficult. So based on our experience with servo drives, we were already working with them at the time. We came up with our own control boards and our own layout for this.
in particular, as you may recall, you've seen this control unit in other videos.
It's just that here, they're a little different. Back then, those boards were installed. Then we decided to put our own boards, our own brains, into this module. And essentially, we left only the power module units themselves. So basically, these are power transistors with some microchips that turn them on and off. It turned out to be a pretty versatile thing which we use in many experiments. It allows us to deliver a high current up to 450, and when stationary it can hold 650 at voltage. The power modules are installed at the bottom, and here's the control board itself. We connect the programmer. That's it. Now it's flashed and we connect the feedback interface. For this motor, it's an incremental encoder. So now we'll be setting it up and checking how it works, because we still don't know its resolution. And accordingly, we also need to figure out the power supply for it, since it's most likely turned off right now. There's also a magic thing, a ferrite ring on the wire. Many people underestimate them, just like I used to. But in situations where there are strong impulse interferences, surprisingly it actually helps. It doesn't let these interferences through, not even along the ground or cable shielding to the outside. We also use an additional optical galvanic isolator. It completely isolates the USB interface, both for ground and power. Technically it's not strictly necessary, but we use it because we're powered by a 380 volt main supply, and our power supply isn't galvanically isolated. In other words, we have an auto transformer. And additionally, to protect the electronics and the laptop, well, just in case, it's better to use it, and it's safer for us as well. Now we'll invite Mikhail and start connecting the power. And
Where's our group? Mikhail, let's get acquainted.
we're supplying power. The red light is an error indicator. Right now it shows that there's no high voltage. In other words, no power to the power section. Now I'm trying to start the encoder, or more precisely, to get the system to work with the motor position sensor. Misha, please turn the shaft, try to rotate it a little. I want to measure the voltage at the encoder outputs to take a look. What's the actual value there? Because for me it only shows discretely, either a 1 or a 0. All right. There's already some metal shavings in there. I'd like to put a little load on it right now. It's 17 volts now, output voltage.
We don't have anything to load it with, do we?
The torque doesn't matter, I'm just controlling the RPMs. I can give it a lot of current, really a lot.
How much do you want from us if you could let us know?
120 amps.
And at maximum, it draws 500 amps per phase. All right, let's add some load now. Let's lower the RPMs.
13, 12.8.
So, you see, you need to reduce the slip a bit at low RPMs.
Lower, give me more torque.
I'm telling you, that's it. This is the most I can do. If
you spin it at 13, it's better to rev it up to 1,500.
Well, yeah, it's a 5,000 RPM motor. I think you need to spin it up to 7,050 at most to get the power out of it. Let's take a look. Right now, if there's 120 amps per phase, that's 750 radians per second.
Well, there it is, yeah, up to 70.5. I don't know what's up with the blue one.
Its power is 12 kilowatts.
So gentlemen, what conclusions have we drawn? Well, in my opinion, asynchronous motors for electric transport have a right to exist, but the way they're used, it's not something we invented. As for the Slavyanka super winding, well, we didn't really see anything new here. For example, as Mikhail tells me, in some spindle drives from ABB and so on. A star-delta connection is used, it's just not labeled as such. Breakthrough technologies there and so on. There's nothing groundbreaking about it, it just reduces the end winding part, saves copper, but winding it is a hassle. It doesn't really lead to anything better. Compared to BLDC motors, the efficiency is 5 to 7% lower. Because of this, there are problems with heat dissipation. In this kind of design, running continuously at room temperature, I think it probably won't be able to handle more than 5 kilowatts before it starts to overheat. If we add a water cooling jacket, then maybe it could handle 15 kilowatts. Compared to BLDC, it's definitely more affordable, much easier to manufacture. And it has a greater capacity for handling short-term overloads. That is, you can pump in a large current and get a high torque for a short period. That's fine for vehicles. The topic of synchronous motors is interesting. We'll try something, I think, rewind one ourselves, set it up and test it. But honestly, we really didn't see anything remarkable or groundbreaking from Mr. Duyunov. It's just an ordinary motor. No better or worse than any other. With that kind of cooling system, it really won't last. It's just completely nonsensical, because it has neither fins nor a fan. What the manufacturers meant by the rated value, only they know. Maybe if it was floating in liquid nitrogen. On some moped, electric moped or bicycle, I think it would work because the peak loads are only at startup. But that's still not the rated value. For example, when we calculate the rated value for our motor, it's for continuous operation at room temperature, basically indefinitely. And so that the windings don't heat up above 80 degrees. That's what I consider the rated value.
Now, if they wrote S1, S1 imposes certain requirements, but rated value is just a word.
So at that point, we achieve the best efficiency. That's 80% roughly speaking for the whole system, yes. But if you exclude the controller, well, you can add about 3% more, 83%. On our motor, we got 93%. How much did Golden Motors get? 90, I think, 91%. By the way, the guys from Golden Motors are really honest. Their numbers matched exactly with their table. Well, basically, that's about what we expected. The problem is, you have to dissipate almost twice as much heat. That's a real issue during heavy-duty operation. If you use liquid cooling, maybe it's not that bad, but with air cooling, it's definitely a problem. But at least there are no neodymium magnets. It's an interesting topic, and we're going to dive into it. A bit later, I think we'll probably test it up to 90 if we get around to it as planned. And soon, in the near future, we'll also be testing the axial flux motor from the competition, which is something we're looking forward to. It's rated at 25 kilowatts nominal and 50 in overload. It's such a beautiful thing. I think it will pleasantly surprise everyone. The size isn't very big. It's rated for 400 volts. We'll see how it spins, but it has a high RPM. Do you remember how much? 12? Is that it? 13, right? Well, we'll need to do a bit of magic with the balancing so it doesn't fly apart. Everything to hell. Just like that. So stay tuned. It's going to be very interesting.